No idea, because
Good. Then let's start with the next session. So the sensory event-related potentials that we discussed in the previous 2 hours are essentially the responses of the brain as observed with EEG to basic sensory stimuli. And the important thing is that you always have an external stimulus delivered to the brain via the senses, and then you observe these evoked potential time series in the EEG. The cognitive event-related potentials that we discuss next are in some way also related to external stimulation, but the focus is not so much on the effects that you see from the external stimulation, but the effects that you observe because the brain somehow processes these stimuli and reacts different to the stimuli if they are presented in different contexts. So it's definitely, if you think in terms of a hierarchy, it's one step away from the pure sensory stimulation. The most important thing about these cognitive event-related potentials that will get clear from discussing them is that they are related to something changing with respect to the expectation of the brain, or something that comes up in a surprising manner with respect to the expectation of the brain. So these are typical responses that relate to some form of prediction error. And this is also not that surprising if one thinks about it, because if things remain the same all the time, why should the brain respond all the time? This would be very energy consuming. So it's of course much more energy efficient if you detect and respond to and process changes. And once you have processed the change, then there's some status quo again, which you don't need to signal explicitly until something again changes. And this is kind of it's similar in the sensory evoked potentials to the degree that of course sensory stimuli coming up are also something novel in the environment, but with cognitive event-related potentials it's kind of higher level changes, or second order changes, if that means something, that drive these potentials. And these cognitive event-related potentials, like we discussed in the history section, they started to become, or they generated interest in the 1960s, and since then have been around. What I am also quite interested with respect to these event-related potentials in, that's a little bit weird English, is that there have been many psychological theories of what they are about, but few computational theories. And so they are like a nice playground for sharpening your computational modeling skills if you do a master thesis and likely a PhD on these, because there is work on the computational modeling of these cognitive potentials, but not much, and apparently it's also not that easy to do that, or at least that's what my personal experience is. So I've started doing some computational modeling of the mismatch negativity around 9 or 10 years ago, and after we did an initial study on this, we had a couple of PhD and also master students, and turned out not to be that easy to get a whole project, including the computational modeling, done. But this, I guess, depends a little bit on the people and how much energy and work they are interested in putting in. Because if you want to do computational cognitive neuroscience, you have to basically do double the amount of work as compared to people who just do cognitive neuroscience. Because once you observe an effect in computational cognitive neuroscience, that interesting work starts, because you start to set up a model and fit it to the data and think about your model and formulate it and write it down. Where in cognitive neuroscience you are done once you have the effect. So maybe that's one of the reasons why people struggle a little bit with it. But there's a lot of things to be done. So that's what's interesting in terms of cognitive modeling. In terms of sensory event-related potential, actually, there's a lot to be done in terms of biophysical modeling, which could then also be applied to the cognitive event-related potential. So a lot of work to do, but you need to know what you're doing. Good. There is a scheme that I use to introduce these cognitive and then also the movement-related, event-related potentials, which is also helpful as a guideline for you when you learn about them, because these cognitive event-related potentials, they always come with a standard paradigm, usually the paradigm in which they were also first observed. So in which context is the respective event-related potential elicited, and what are the typical stimuli that are used to elicit these kind of event-related potentials. And we will discuss that for the 4 cognitive and the 5th movement-related ERP. Then, very similar to the sensory evoked potentials, the question is, where are these ERPs actually primarily seen and when? So which electrodes are most involved, and when after stimulus onset can these effects happen? That's essentially like for sensory evoked potentials. With respect to the generating cortical systems, it's in a way even worse than for sensory evoked potentials, where at least the first and the early components one can pinpoint quite well. There exist theories about the generating cortical systems, again coming from dipolar source reconstruction analysis, and we will introduce those, but it's more like this is what people think. It's not as a hard fact as Arthur Jacob said that comes out of a scanner. There were certain things on Wednesday which were a little weird. And then these cognitive ERPs, of course, also have some kind of neurocognitive story associated with them, which goes a little bit beyond what we had for the sensory evoked potentials, because there the stories mainly a stimulus elicits some peripheral activation, which then is relayed to the cortex, and there some activation is elicited. Here we have a little bit more of a neurocognitive story. As I said, this will usually be something like a violation of expectations or a prediction error in a very general meaning of these terms, not in terms of something too formalized. Good, so this is kind of the 4-step thing that we want to discuss for all of them, and which is also something good to know. And we start with mismatch negativities. So mismatch negativities, has anyone heard about mismatch negativity? Yeah, in which context? Cognitive neuroscience as well. No. Do you remember anything about them? Which is good, otherwise we wouldn't have to do this now. So obviously the name already says there's something that doesn't quite match, so there's a mismatch, and apparently there's some negativity, but already note that although these are actually, whenever one talks about them, these are negativities, but with the polarity of EEG, it depends, but actually these are always negative. So, like I said, so these cognitive event-related potentials, they are tied in with certain paradigms. And the typical paradigm that is used to elicit mismatch negativities is the so-called Oddball Design, which we've already seen in this little figure by Luck. And the typical oddball design that is used or was also originally used for mismatch negativity is an auditory oddball design. So in this case, tones, pure sine tones usually being presented to the ears, so just beeps essentially. In this oddball, and the point of this oddball design is that there's a sequence of similar stimuli referred to as standards, and sometimes an deviating tone occurs, which is then referred to as a deviant. So something like do 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 do, something like this. That's the oddball design, which of course you can also have in different modalities. So we did quite some work in somatosensory, in the somatosensory domain. Also in the visual domain, the mismatch negativity has been described. The most important thing in terms of the cognitive processing about mismatch negativities is that people, so the participants, do not attend to the stimulus train. So they are not, for example, counting the number of deviants, or even worse, if you want, respond to the deviants, but they attend to something different. So a typical setup for this is that you present these trains of tones, and people watch a movie at the same time, usually a silent movie then, so Shaun the Sheep, something like this. So that you don't have any auditory interference, but you also don't, you're not asked to attend the stimulus and actively process anything about the stimulus. Then if you do that, what is observed is a negative deflection for deviants versus standards around 150 to 250 milliseconds per stimulus, and mainly over frontocentral and central electrodes. So this centrality here has a lot to do with the fact that the typical paradigm is binaural stimulation. When we do mismatch negativity studies in the somatosensory domain, using, for example, only a one-sided, so for example left median nerve stimulation, then actually these mismatch negativities also get lateralized. But the typical thing that you will find in reviews or papers about mismatch negativities is that they have been evoked by binaural, so the auditory stimulation to both ears, and hence the negativity is central. Cortically generating is mainly auditory cortices, so bilateral supratemporal processes, and maybe something frontal. I will show you some evidence for that in a second. The interpretation then is that mismatch negativities relate to the automatic and pre-conscious processing of unexpected sensory input, and this automatic pre-conscious processing is kind of was emphasized or is related to the fact that people don't attend to the stimuli, so they couldn't really tell you much about them, and that it's also happening quite early, where the idea is that we are not really aware of that. But that's quite tricky actually. So the more important thing is that it's that people don't attend to these stimuli, and yet there is some difference observed with respect to different stimuli. So this is now an example from the Nährtannen review of, oops, sorry, somehow my PowerPoint is not quite right. I have two open. Oh, it's all gone. This is an example from the Nährtannen review. Nährtannen is kind of the godfather of mismatch negativities. And it shows that mismatch negativities vary with the deviancy, if you want, of why does this not go away? There we go. The deviancy of the stimulus. So the story is here that there are 80% 100 Hertz tones presented to participants, and what is shown here is the peristimulus activity of electrode FZ, so it's a central electrode here, and in these 80% 100 Hertz tones, interspersed are 20% of these deviant tones, and these deviant tones, in terms of their physical deviation, increase from 1004 Hertz to 1032 Hertz. And compared to the 1000 Hertz tone standard, for relatively strong deviance, there is a mismatch negativity observed. This is, of course, Natanen, who's an old person, and hence plots negativity upwards, because he's old. And this negativity here is then this, which looks like a positivity because it's plotted invertedly. And one can, of course, also compute the difference between the standard and the deviant trace for this electrode, and then for this very small deviation, one doesn't see much. But as the deviant stimulus gets stronger, one sees more of a negativity here, which is plotted upwards because we are EEG scientists. What you will also notice is that there is not only this effect at 150 to 200 milliseconds, there's also something here happening a bit later. So I think this doesn't relate to... What's this actually? So this is this positivity here, which looks like a negativity, but is a positivity. So with the mismatch negativity, the common thing is, so it's around 150 milliseconds plus minus after stimulus. From my perspective, the entire response, so if you look at this comparison here, deviant versus standard, there are differences all over the place. So here very early on you don't see much, but then it's, the curves are just not as well aligned as these two curves, for example. And I then started to call these things more mismatch responses or something, but not negativity, because there are also these positivities. So that's some debate you have in the EEG literature, and some people say, we shouldn't focus on these kind of very short time windows and talk too much about them, because if you have differences between conditions like here, this is usually over to varying degrees over longer time windows, and essentially the entire peristimulus time window. This shows some of the, so quite an old, I think, from 2000, source reconstruction of this, where here you have the skull potential distribution, fairly old school with hardly any color, and some source reconstruction where you use essentially many dipoles at a lot of places. We will also discuss that in more detail. And the idea is that here, with increasing time after the stimulus onset, this negativity, which is just this activity here, this negativity shifts a little bit from supratemporal, so auditory cortices, to more frontal cortices. But it's fairly light, and it's some big blob of activation around the central fissure. You see also that the scalp topography doesn't really change that much, but the story is nevertheless this must be something wrong. Should be a later time point here. Good. What else do we have? Yeah. So this is again data from myself in somatosensation, where we actually did effects a little bit different. So we wanted to go away from these oddball designs, because one of the disadvantages of oddball designs is that, of course, you have many more standards than deviant stimuli. The best thing to do actually in this case is to take as standard only the ones that are the stimuli that happen immediately before a deviant, so that you have the kind of same number. And the other thing is, of course, that if you have standards which are all the same physical stimulus, and then you have a deviant stimulus which is a different kind of tone, then you not only have the case, it's not only the case that these stimuli are unexpected because they only happen in 20% of the cases, but they are also physically different. And of course, you're much more interested in the unexpectedness as compared to the physical difference. And this is, of course, in the standard oddball, this is not decorrelated at all. And what we hence did is that we had two somatosensory amplitudes and used what is commonly referred to as a rolling paradigm, where the deviant stimulus is always the one that reflects a change. So if we have high amplitude and then we go to low amplitude, then this is the deviant. And for some time we have low amplitude and then we go to high amplitude, then the high amplitude is the deviant. The nicest way to actually represent this is not what is shown here. So this is the average over the high and low amplitude deviants. So let me zoom in. So deviant, and the deviants refer to both the high and the low amplitude stimuli, and the standards also to both the high and the low stimuli just before a deviant stimulus. The best way actually to represent this is, or a better way to represent this is to show both the high amplitudes and then in the context of it being a standard and in the context of it being a deviant. And the same for the low amplitude stimuli, because the response to the high amplitude stimulus is of course larger, irrespective whether it's high or whether it's a deviant or standard. It's higher the response than to the low amplitude stimulus. But again, you will see this negativity for deviants at both the in both the high and the low amplitude conditions. So this is average over both amplitude conditions, and then you see the average effect over both amplitude conditions, and you see that, like I said, so the standard, the deviant definitely has a negativity here a little bit later at 200 milliseconds. What we also observe here is quite a strong P300, which had to do with the fact that actually in our mismatch negativity paradigm here, people attended to the stimuli in some way, which was not optimal. But we still see this early negativity effect. But what I also want to stress again from these data here, there are differences not only in the typical time window of 140 milliseconds, but there are also earlier and in this case quite strong later responses. Basically, so somatosensory mismatch responses had been reported previously to when we did it, but there were only like 5 papers or so, and now there are like 8 papers. So it hasn't really changed, but it's a little bit a niche thing. Typical thing being the auditory mismatch negativity. Yeah.
What do you mean by high amplitude stimulus? Shouldn't it be a high frequency? Like, is the amplitude different or the frequency of the tone?
In the auditory, these were frequencies, so these were high and low tones. In our somatosensory mismatch response, this was the amplitude. So there was just a single pulse of a stronger amplitude and a low amplitude. Yeah, and then we actually did some basic modeling of that in this paper. And following up to this day, so there are now 2 more PhD students. So at one point, I think it was decided that if one person who is not me cannot do this, why not have 2 PhD students working on it? Maybe it gets better. Yeah, the problem is that, like I said, when everybody is done, because you have something like this, then in computational cognitive neuroscience, you need to work more. And then it's like, but they are already done. Yeah, but you wanted to do computational cognitive neuroscience. Yeah, but I just want to anyway, good. P300. The main difference between the P300 and the mismatch negativity actually lies in the paradigm, or let's say it actually lies not so much, it lies in the paradigm, but there it lies with the participant. So the standard paradigm for P300 are also oddball paradigms. So again, you have 80% of one stimulus and then 20% of another stimulus, or you do roving paradigms where both the physically different stimuli can occur in the deviant or standard condition. The main difference is that the participants are instructed to mentally or physically respond to the deviant stimulus. Right? So in the typical mismatch negativity paradigm, not the one that we did, but in the typical mismatch negativity paradigm, people are not supposed to attend to the stimulus at all. In the typical P300 paradigm, people are told to respond to the stimulus, often even by pressing a button. So whenever a target stimulus comes up, they press a button, or at least to mentally respond to the stimulus, for example, by counting the number of deviant stimuli or the number of stimulus changes if it's a roving paradigm. And then if by varying paradigms in this regard, there can also there are different aspects to the P300. Namely P3A and P3B. So in general, the P300 is a positivity over midline electrodes in response to all sorts of sensory stimulation. So you can have that for auditory, for visual, or for multisensory stimulation. It's a positivity. It's around 300 milliseconds per stimulus. It's a little bit larger in parietal as compared to frontal electrodes. And then it comprises at least 2 subcomponents referred to usually as P3A and P3B. So P3A being the first one, more towards the 250 milliseconds per stimulus, and being again more kind of a deviance detector, not associated with a task, so being more automatic, and the P3B being what some people actually call the P300 proper, which is a task associated longer latency amplitude deflection. Cortical generating system, a parietal temporal frontal network, which is essentially the whole brain. And the interpretation then is that this is some novelty processing, but not automatically and pre-conscious, but task related. So here's an example for different kinds of paradigms that one can do. All of this is taken from this Polich review in Clinical Neurophysiology from 2007. So here, this would be a single stimulus referred to as target, and the participant has the task to press a button when the target appears. And what is then observed is usually a peak 300 milliseconds after stimulus onset. This has to do with both the stimulus and actually the response. So if we go briefly back to what I've shown you earlier in terms of visual responses, this. So here people had to do a perceptual decision, like Marius Philostheos told you about on Wednesday. They had to decide, is it a face or a car? and they pressed a button. And then whenever people press a button to some stimulus, you get these kind of strong positivity in the central parietal electrodes, around 300 milliseconds per stimulus. And this is also what we observe here, although this is now not an oddball paradigm, but it's this response to a stimulus. Now going back to where we were. So then this is kind of responding always to this target stimulus. This is the more typical P300 oddball design, where you have 80% standards and then sometimes a target stimulus, which is easy to discriminate and is associated with a strong P300 component or amplitude deflection, and this is the stimulus, the standard stimulus trace. Now what is shown here is the attempt to dissociate the effect of the deviant stimulus from the effect of responding to the stimulus, because like I said, in P300 paradigms, this is usually correlated, so that you attend to deviant stimuli and usually respond to them by pressing a button. And here, this shows now the response to doing this stimulus discrimination and responding to the target, which primarily elicits this P3B response, while a distractor stimulus that is not responded to but is quite different from the standards elicits this earlier P3A peak. So the P3B is more related to the response process to the stimulus, while the P3A is more related to the novelty of the stimulus, which makes some kind of sense if you think in terms of the temporal order, that also mismatch negativities are earlier than P3A, then P3A also respecting kind of the novelty, and then the later P3B response, which of course is, if you do these kind of stimulus response tasks, is roughly around the time that people actually press the button. So that's then, so you know that the fastest reaction times that people usually have are around 300 milliseconds, but then it's actually more normal to be a little bit slower, so around 350, 450 milliseconds, which is then around the time of the P3B. Yeah. So it's relatively natural how these responses come about. So distractor stimulus with no response P3A, and target stimulus P3B. This is an example also again from EEG fMRI study by Tom Eichele from 2005. Where he looked at the single trial covariation of P3 activity with fMRI activity, and essentially found most of the brain, or the typical areas that always go on when people do something. So some parietal activity, some temporal activity, some frontal activity. If one looks at, do I have a picture of that? No. If one looks at the topology of the P300, one basically sees a large blob of red, sort of positivity, in kind of parietal frontal areas, and one doesn't really see like a dipolar pattern or any interesting pattern, but it's more like it looks like that that most electrodes show a positivity, and hence pointing that to specific brain areas is then quite difficult. But also, if you think about what kind of processes are involved, it's also things like motor preparation, the motor response, and this entire step between these entire steps between processing of the stimulus in terms of its sensory aspects and then responding to it, selecting a response and so on. Hence you would think that actually most of the brain is involved in not only a single brain area. Yep.
How to disentangle attention? Well, you said that the difference is one reflects more the response and the other one more the modality of the stimulus. But can we just more attention paid to the target and the distractor?
It's a good question, and there are studies that even coming out these years that try to disentangle expectations and attention and so on. I think in this case, of course, with attention, you also always have these kind of two aspects: bottom up and top down attention. And here one can say things like, for example, this difficult stimulus discrimination requires a lot of top-down attention, so you need to really pay attention to whether there's a difference, whereas the distractor stimulus is kind of this salient feature that just captures a lot of attention. And so I would say, so one could argue that actually in both cases you have the same level of attention, just being of different forms, bottom up and top down. Attention is that's kind of I think it still is basically you can, whenever somebody gives a cognitive neuroscience talk, you can always say, but isn't this just attention? And then I think the answer is usually, I don't think that attention is a very useful concept or something. But you're right, and this is, I think, also the case that Pia made on Wednesday. Ideally, one would try to disentangle more aspects and somehow think about experimental manipulations that let one. So, for example, I think it's to dissociate the expectancy of a stimulus and the attention given to a stimulus. One can come up with experimental designs where you, for example, spatially attend and then also orthogonally to it manipulate how often a specific stimulus occurs and so on. And then one needs these kind of experimental manipulation to say something more. Here, in this case, of course, attention is not an explicit experimental factor, and hence it somehow plays into both. Well, other questions? No. Good. But the important thing again about P300 is that P300 is associated with attending to the stimulus, and mismatch negativity is associated with not attending to the stimulus. So that's the bottom line there. Good. Then something that I also got involved recently with Milena Rabowski, who studies language, and also had an interest in basically explaining language event-related potentials using some form of probabilistic models. So language-related event-related potentials. So these again have to do with some kind of unexpectedness, surprisal, or prediction errors. The standard paradigm for language-related ERPs is actually not that people read Harry Potter or some kind of text, but that they are exposed to words at a 1 Hz frequency. So one word comes up, goes away, next word comes up, goes away, and so on. And then there are two classic effects that are associated with these kind of paradigms, namely the N400 and the P600. So the N400 is evoked by violations of semantic expectancies. So a typical thing here is while I was visiting my hometown, I had lunch with several old shirts, versus while I was visiting my hometown, I had lunch with several old friends. Of course, this several old friends is more expected. And then what is compared is the event-related potential in response to this last word here. Yeah? So here, for each word which is presented for 1 second, you have an event-related potential, and the difference here is between this word and this word. And then you see the N400 effect by the violation of semantic expectancy here then with the shirts. Then there's something like P600, which relates to syntactic violations. Again, in this word-by-word paradigm, the broker persuaded to sell the stock, which is syntactically wrong as compared to the broker hoped to sell the stock. So if you then compare persuaded, there's something syntactically wrong. This two to this two, you see a P600 for this. I will show you P600, it's a little bit iffy. The N400 I think is more reliable. N400 is a negativity wave over central and parietal electrodes, obviously 400 milliseconds post critical word, and it's slightly larger on the right than the left hemisphere. And I think the story goes that although language is more associated with the left hemisphere, this activity of the left hemisphere projects stronger to the right hemisphere, and hence it's stronger on the right hemisphere. But I'm not very good with this whole lateralization of brain activity. And the P600 is a positivity, obviously 600 milliseconds post critical word. Yeah, and the generating systems being activity in left temporal and frontal lobes, so again relating to auditory cortices and the language centers like Broca and Wernicke. And of course, this has been, and this is actually interesting, so this has of course been interpreted by the language community as some neural signature of semantic processing, and the way, with Milena and our work, we think about it maybe a little bit more general in terms of expectation violation. So that there isn't something that is specifically language related or meaning related, but it's just that like everything that the brain encodes certain environmental statistics and knows what to expect, and if these expectations are violated, like in the deviant and standards, in the mismatch negativity paradigms, then it responds more strongly. So, this is kind of a, let's say, more modern or more integrative interpretation than to say this has to do only with language semantics. So this shows an example for the N400. Again, there are these words presented every second here, so every second, and it was his first day at work is kind of a normal sentence, gets this full line, whereas he spread the warm bread with socks, elicits this negativity. Again, this is work from the 60s where people in EEG I don't know, were walking on their heads, or for whatever reasons they plot negativity upwards, and you have this negativity here. This P560 is actually something it's actually not from the 60s, sorry, it's from 1980. So it's almost as old as I am. But still negativity is upwards. And this is the N400 to this word socks. This P560 you can ignore. This is actually the thing that is observed for the, or when I looked around, so I wanted to find something for this lecture that is kind of the original effect, that here is the N400, and what I found with respect to the P600 was this reference from 1992, which related to this, the broker hoped to, whereas the broker persuaded to, which is syntactically wrong, and this is the response to the word to in both contexts, and the P600 is then this here, and to me it looks a little bit less convincing than this, but this is kind of the original effect, and again negativity upwards, so positivity downwards. Good. I would suggest to take a break now. Are there questions by now? No. Good, then one last break, and after the break, 2 more event-related potentials, and then we're done. Yay!